Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about the law of cosines. All right, so our objectives are to use the law of cosines to find unknown parts of a triangle, which we're calling solving triangles. And then we're going to determine when to use the law of sines or the law of cosines to find unknown parts, and this should be 3. And then we're going to use the law of cosines to solve real-world problems and application problems. All right, so let's go back and let's talk about the congruence postulates. We talked about this before with law of sines. All right, so law of sines, by the way, sine A over A is equal to sine B over B, where the lowercase b is the length and the uppercase B is the angle. All right, so we're going to take a look at this table here, and I want you to create this table. So I'll give you a moment. We can pause. A law of sines in the left-hand column, a law of cosines in the right-hand column, and then the 5 congruence postulates that we had talked about. All right, so let's take a look at an angle, side, angle, triangle, where you're given 2 angles and an included side. And then I want you to use a law of sines to find the missing angle and or sides. And I'm going to pause here for a moment while you figure this out. So this is a little bit of review. So you're going to use a law of sines, not the law of cosines yet. And we're trying to figure out whether or not you can use a law of sines or cosines for each identified triangle based on what you're given. I'm going to pause here. Please solve the triangle. All right, so this is what you should get for the solved triangle. So yes, in fact, you can use a law of sines to solve angle, side, angle triangles. So we're going to say yes here. And then we're going to create a check mark, angle, side, angle. We can use the law of sines. All right, angle, angle, side. So you're given 2 angles and a non-included side. We're going to use the law of sines to solve. And you're going to be able to solve this triangle as well using the law of sines. You can check your work here. So yes, again, we can use law of sines for angle, angle, side triangles. Moving on, we're going to look at the angle, side, side triangles where you're given an angle and or a non-included angle and 2 sides. And so I want you to solve this triangle. Remember, you can have 0, 1, or 2 solved triangles. So I'm going to pause here. All right, so in this case, you end up with 2 solved triangles. You get initially 56.4 as your reference angle. You see that 123.6 will work in the system. So you use those 2 values to find the remaining values of the triangle. All right, so we're going to say with caution, you're using the law of sines to solve triangles in which you're given the angle and then the 2 sides, or the 2 sides of the non-included angle. So we're going to create a check mark here with an asterisk, meaning caution. I'm going to give you another problem for solving a triangle. Again, angle, side, side triangle. So pause here for a moment. Please solve this triangle. Okay, you're going to see that in this case we're only going to get 1 solution because the second solution provides you with an angle measure of 134.4, which when added to 75.4 creates a triangle that's greater than 180 degrees, whose internal angles are greater than 180 degrees. So we just have 1 solution in this case, 45.6 for the angle measure, 75.4 for the other, 13.55 for the side length. All right, so now we're going to go to side, side, side. Let's see if you can solve for a side, side, side using the law of sines. So we're going to realize that you cannot solve using the law of sines a side, side, side triangle because you end up with no defined ratio. You need at least 1. Which means that you'll end up with 2 unknowns if you use the law of sines. So we're going to say no to side, side, side. Then we're going to try side, angle, side, same thing. I'm going to pause here while you try to work this problem out. And you're going to see that, again, you have an unknown in each of the ratios. So you're going to end up with 2 unknowns. Again, you need 1 defined ratio in order to solve. In this case, we don't have any defined ratios. So we're going to say no to side, angle, side. All right, so let's talk about the law of cosines. I'm going to provide this to you here. I'm not going to go through the derivation of the law of cosines. I'm just going to give you the formula. Please notice the pattern to help you memorize the formula. So please write this down while I pause, or you pause. All right, so now we're going to go back through the sets of triangles, side, side, side. Now you're going to use a law of cosines to find the missing angle side lengths, but in this case, let's just find the measure of angle C. So I'm going to pause here while you figure that out. All right, so here is the work that goes into it. My strong recommendation is you give yourself a lot of space to work out law of cosine problems because there are a lot of calculations, small calculations that need to happen as part of the process of deriving whatever value you need to derive. It could be C value, it could be C, the length C, or it could be the angle measure C. But you need to choose a correct equation and then solve for that given unknown variable. And again, please give yourself a lot of space to do the calculations. So 114.5 degrees is the angle measure. So yes, we can use the law of cosines to solve for side, side, side. So I'll put a check mark here. Side angle side, please solve just for length B using the law of cosines. All right, and you can see that we end up with 9.32 as the side. So again, yes, we can use the law of cosines to solve. And of course, at this point, it's probably easier to use law of sines moving forward to complete the solution for the rest of the triangle. And I'll leave that up to you to determine as you move through each of the different requirements for each of the parts of the triangle. So we're going to say yes, we can solve it. So check mark here. Now we're going to try angle side side. So I'll pause here. All right, so what's going to end up happening is you're going to end up with a quadratic, and you can use a quadratic formula to solve for A. However, in this case, it's probably easier just to use the law of sines. So we're going to say it's too much work to use the law of cosines to solve for angle side side problems. So just use the law of sines, but of course, be careful. So we're going to say this is too much work to do in general. So we're going to put a check and then a minus next to ASS. Angle side angle. I'll pause here while you try to figure this out using the law of cosines. All right, so we end up again with two unknowns, so we cannot use the law of cosines to solve for an angle side angle triangle. So we're going to say no. We're going to answer no in the box. We're going to move on to angle angle side. So I'll pause here while you try to figure this one out. Just find the A or B lengths. And of course, we end up with two unknowns, so we cannot use the law of cosines to solve for angle angle side triangles. All right, so it's not going to work. We end up with this table. So my expectation is for my students to understand the table and then understand when to use the law of sines and cosines based on what's given in a particular triangle. All right, so we're going to end with an application problem. We have two airplanes, and we can consider this a two-dimensional diagram. Two airplanes at points A and B. They have elevations of 26,000 and 17,000 feet respectively. Both are flying east towards an airport. Here's the airport, which we identify as T. From T, the angle of elevation of airplane A is 5 degrees. So the total angle of elevation 5 degrees. And from B is 2 degrees. How far apart are the airplanes from A to B? So I'm going to give you a moment here to work this out. I'm going to pause and then come back and explain it. All right, so we're going to use the law of sines. We have angle, angle, side. So we're going to use the law of sines to solve, and then you can use the law of sines again to solve. Or you can use the Pythagorean theorem. So let's go through the the law of cosines to solve in the second round. All right, so let's go through the problem. We're going to solve first for BT. So sine 2 over 17,000 is equal to sine of 90 over BT. And we end up with BT is equal to 487,113 feet squared. And then we're going to find out what CT is. CT is going to be 17,000 feet squared plus CT squared. So CT ends up being 486,816 feet. So, I'm sorry, BT ends up being 487,113 feet. And we're going to use the Pythagorean theorem to solve for CT, which ends up being 487,000 approximately. Now we're going to solve for AT. Sine of 5 over 26,000 is equal to sine of 90 over AT. AT ends up being 298,316. We're going to find DT by using the Pythagorean theorem. DT ends up being 297,181. All right, so we have several ways to solve this. We can use BT, and we can use AT, and then we can use the difference between the angles here, and we'll have a side angle side component here, which we would use the law of cosines to solve. But the way that I'm going to do it is I'm going to take the difference between CT and DT, which is CD, and then I'm going to create another triangle here from B to E to A. So BE is a parallel length here. It's the horizontal length, the path of currently of the airplane B. And then I'm going to find the length A to E, which is the difference in altitudes, or 9,000 feet. And so using CD as BE and 9,000 feet as AE, I have a right triangle, and I'm going to use that right triangle to solve for AB, which is the hypotenuse. So AB squared is equal to CD squared plus AE squared. AB squared is equal to 189,635 squared plus 9,000 squared. And then AB ends up being 189,848. And again, you can use the lengths AT and BT and this angle measure of 3, and then use the law of cosines side, angle side to solve for the length AB. All right, but you should get the same answer, 189,848. That's it for this edition of Ott Math. Please come back and join us when we talk about more applications problems in Chapter 9.5.